Hello friends, my next section is active filters. So why the name active filters? Actually the name active filters because filters are used in signal conditioning and mainly operational amplifier as the component of that one. So what do you mean by signal conditioning? See, signal conditioning in the sense I have a certain frequency component signals, that is I have certain frequency component signals. So if I give this signal to my operational amplifier which is configured as a filter, based on the type of the design, my operational amplifier will allow only low frequency component to the output, or it can allow only high frequency component to the output, or it can allow only particular range between F1 and F2 component to the output. So this process is called as filtering. So now based on the design, there are low pass filter and there are high pass filter and there are band pass filter. First one is called as low pass filter. It will pass only low frequency component. Second one is called as high pass filter. It will pass high frequency component. Third one is band pass filter. So three types of filter classifications are there. So now we will see. First one is non-inverting unity gain low pass filter. So the diagram you can see here. See, operational amplifier, we have connected the output directly to the input. Output as a feedback to the input without any feedback resistor. That means it is a unity gain. It will not amplify actually. It is a unity gain. It is called as unity gain. It will not amplify. Understood or not? It is not amplify. It is a unity gain. Now, here we are giving input signal which contains certain frequency component with through resistor R and capacitor C1 to the non-inverting terminal. Now here capacitor C1 is connected in shunt or in parallel. So now how this works? We know what is capacitor provides. Capacitor provides capacitive reactance. What is that? Capacitor provide capacitive reactance. Capacitive, I can write here, reactance. Capacitor provides capacitive reactance. How you mention capacitive reactance? Here you can see the formula for the capacitive reactance is this one. Capacitive reactance. The formula for the capacitive reactance is 1 by 2 pi FC. FC is frequency. So now when the frequency is 0, if I take for lower frequency component, if FC is 0, what is the value of 1 by 0? 1 by 0 is infinity. That means this will provide infinity resistance. So low frequency component cannot move like this. It has to move like this only. So this is our low pass filter. Now how you can design the cutoff frequency? Cutoff frequency FC, cutoff frequency you can design by using this formula. What is the formula for cutoff frequency? FC by 2 phi R and C1. By using this one we can decide what is the low cutoff frequency the particular amplifier or this can allow. That is called as non-inverting unity gain amplifier. So move on to the next one. So next one is non-inverting active filters. It is also low pass filter only. Non-inverting is voltage gain. So what is the difference between the last one and this one? Here we have connected feedback resistors in the form of voltage voltage divider configuration and whatever the input we will get gain for that one. Normally you have to remember feedback is always connected to the inverting input only. So what is the gain we will get here? This is the gain you will get here. And once again cutoff frequency is designed by 25R3C1, and you have to remember this is also low pass filter. Moving on to next one. Inverting with the voltage gain. The last one we saw was non-inverting. Now this time it is inverting with voltage gain. This is also low pass filter only, and you have to remember here the gain is this is the gain, and cutoff frequency is designed by like this. This is the gain. AV is equal to minus R2 by R1. Now high pass filter. Now we will move to the second section, high pass filter. Here you can see here in the high pass filter, this is the non-inverting with the unity gain. This is the unity gain. How it works? Here you know capacitor is now connected in series. Resistor is connected in parallel. You know capacitor will block DC component, that means low frequency component. Only high frequency component it will allow. So it is a high pass filter. So and cutoff frequency is designed by like this, and gain is 1. Now we will see the different this one. Under this one different so non-inverting with the voltage gain. So same configuration. You have to remember here what is the voltage gain. Non-inverting with voltage gain for high pass filter. So non-inverting with voltage gain for high pass filter. These are the diagrams for inverting with voltage gain for a high pass filter. So now the last one in this category is second order high pass filter. Second order high pass filter. Here the components Z1, Z2, Z3, Z4 is C, R, and Z1, Z2, C, and Z3, Z4 is R to get second order high pass filter and to get second order low pass filter. So this is the diagram for generalized form of second order filter, high pass and low pass filter. So with this student, now we will move to the one numeric in this category. So you can see here the numeric. So refer to the first order low pass filter. He says here, refer to the first order low pass filter. Refer to the first order low pass filter. Determine the cutoff frequency. You have to determine the cutoff frequency and determine the gain at the value 4 times the cutoff frequency. This the diagram is given. So what is the diagram given here? My dear students, you see we have inverting. We have inverting with the gain. Inverting with the gain you can see, and it is it says low pass filter because capacitor is connected somewhere here. Capacitor is connected somewhere here. So low in the shunt in parallel, it is a low pass filter. So we have input is given here, and this is the resistance, and this is the feedback resistance. So my dear students, we remember. So this is, suppose if I draw, this is the frequency and this is the gain. We know normally gain is let you take the gain at 0 frequency, and later gain will decrease at 3 dB, and later it will decrease something like this. As I explained previous, it decreases 20 dB per minus 20 dB for a decade. It will decrease minus 20 dB for a decade, because you are you draw this one diagram, you draw this curve by using semi-log plot. There it is called as a decade, or minus 6 dB per octave. So this is the 2 parameter we use here to express gain, octave. So now we will see, first we will calculate a cutoff frequency FC. How to calculate the cutoff frequency FC? So to calculate the cutoff frequency FC, we are using 25R1C1. What is the value of R1 here? R1 is this one, and C1 is this one. If you substitute this value, my dear students, if you substitute this value, what you get here is a cutoff frequency. What you get here is cutoff frequency 2 pi R. R is equal to this one, and C is equal to 1000, see here, C is equal to 1000 picofarad. So 1000 into minus 12, that you will get 15.9 kilohertz. This is the frequency what we get, cutoff frequency. Now gain at cutoff frequency. There is a formula for gain at cutoff frequency. What is the gain at the cutoff frequency? We have to remember the formula 1 by something like R3 by R2. That is the formula we have seen, gain at the cutoff frequency. So gain at the cutoff frequency, when you substitute, you will get 2.11, and in decibels 20 log 2.11 you will get 20.827 dB. Now gain at cutoff point, so it is less than 3 dB. So it is less than 3 dB. So here you can see gain at cutoff is equal to so we will get here 20.83 dB according to the calculation you will get. Now gain at 4 times the cutoff frequency. We have to calculate gain at 4 times the cutoff frequency. You have to calculate. So how to calculate that one? So this is the answer, gain at the 4 times the cutoff frequency. This is the answer. We will get 8.87 from 20. See, this is the gain at cutoff frequency. So now see, this is our curve. This is, see, let me try to explain here. This is gain and this is frequency. This is frequency, right? So this is gain. Now this is gain expressed in AD and decibel. What it says, gain at cutoff frequency. Cutoff frequency is 15 kilohertz, right? Something 15 kilohertz, not exactly. Here gain is equal to 20.83 decibel something. Now gain decrease by 6 dB per oct. Gain decrease by 6 dB per oct when the frequency doubles. That is, here it is FC, and next oct it is a 2 FC, and next oct it is a 4 FC. So when frequency increases from year to year, gain decreases by 6. So from year to year 6 and year to year 6, total how much it is? Minus 12. That you have to subtract. You cannot use here decade. Why? Decade means 10 times. If we ask what is the gain at 10 FC, then you can use decade. But here the question is the gain at 4 times. How you will get 4 times of frequency? First you have to double it. When you double it, that is called as 1 oct. 1 oct means a 6 dB reduction. Then once you double this one, this becomes 4 FC, 2 oct. 2 oct in the sense 12. That is nothing but you will get somewhere here 7. So we will see what is the value we got. So what is the value we got here? 8.827. So in this way we will solve this problem. So dear students, with this we have completed active filters. The next session is something about relaxation oscillator, the application of operational amplifier, how operational amplifier can be used as a relaxation oscillator. Hello student, welcome back. The next topic is relaxation oscillator. This is one of the application of operational amplifier. Here you can see operational amplifier is connected. In the feedback path, resistor is connected and capacitor is also connected. So now the question comes, what is oscillator? A oscillator is the device which produces oscillating signal, either maybe triangular or pulse type. In this case, we are using relaxation oscillator to produce a pulse waveform as shown in the diagram. Now, initially, the capacitor is totally discharged. Now, initially the capacitor is totally discharged. That means the input voltage at the non-inverting terminal is 0. Definitely, the input voltage at the non-inverting terminal is higher. That means this is higher than this one. So, output will be positive, that is plus Vsat. Output will be Vsat. Now, this Vsat output voltage is fed back through resistor and our capacitor will try to recharge. And same Vsat voltage is fed back through our resistor divider network. So now what is the voltage, reference voltage at non-inverting terminal? The reference voltage at non-inverting terminal is nothing but R2 divided by R1 plus R1 divided by R1 plus R1 plus R2 into Vsat. So that is, this component will call B. So then the reference voltage is B Vsat. So reference voltage is B Vsat. So our capacitor will charge from 0 till it reaches this one, positive Vsat. When the voltage at the capacitor or voltage at this terminal is greater than this B Vsat, that means now this one will become greater than this one. That means output will be minus Vsat. Output becomes minus Vsat. When the output becomes minus Vsat, capacitor, same voltage is fed back to the capacitor and now the capacitor will discharge. So capacitor will discharge. Now what output is fed back to the inverting terminal? It is same, but it is B into minus Vsat. When the capacitor voltage goes below this one, when capacitor discharge and it goes below minus Vsat, then this voltage here at positive terminal, it becomes more higher than negative terminal. That time output will get to plus Vsat and capacitor will try to charge in the positive way. So in this way, this will repeat, charging and recharging of the capacitor repeats, and we can see the time period is nothing but this is T is nothing but on period and off period of this pulse waveform. So that is called as T. So there is a formula to find out T. T is equal to 5 RC ln 1 plus B minus 1 minus B. So in the next slide, we will see the numerical related to this one. So relaxation oscillator determine the peak to here the problem is here, determine the peak to peak amplitude and the frequency of the square wave. Saturation output voltage of the operational amplifier is plus or minus 12.5 volt. Here it is given. So here it is given. This is VSAT. VSAT is either positive this one plus 12.5 or minus 12.5 at the power supply voltage of plus or minus 15 volt, and you have to peak to peak amplitude you have to find out, and you have to find out the frequency of the square wave. So how to find out this frequency of the square wave? So first, how to find out this frequency of the square wave? So here you can see the feedback resistor is around 10 kilo ohm, and this is our this one capacitor, and these are the resistors. So first we have to find out B. So we know the formula. First we have to find out B. B is equal to R1 plus R2, that is R is nothing but 47 kilo ohm, and R1 plus R2 is nothing but R1 plus R2 is nothing 57. So we have to find out the value of B. By using the value of B, we got the value of the B is nothing but this is 0.825. That is the value of B. Now we know the formula for the output waveform in relaxation oscillator, that is 2RC ln 1 plus B and 1 minus B. So it is so please remember, this is ln 2RC ln ln and 1 plus B and divide by 1 plus B divide by 1 minus B. That is the formula. So when you substitute this one B, we know you will get the value 4.69 millisecond, and we know frequency is 1 by T. When you calculate this one, you will get 2.13 kilohertz. You will get 2.13 kilohertz. Now we have to find out the peak to peak amplitude of the output. How to find out the peak to peak amplitude of the output? See, this is positive VSAT and this is the negative VSAT, and this is the time, and we found out the frequency also. This is positive, that is says 12.5. So negative is also minus 12.5. So then what is the peak to peak? That peak to peak is nothing but now 25, right? So peak to peak is nothing but we will get 25. So in this way we will calculate this value. So the next one is next one in this category is a non-linear amplifier. So we will see now what is non-linear amplifier. Non-linear amplifier. What do you mean by non-linear amplifier? Non-linear amplifier, in the so far you have seen the linear amplifier. Linear amplifier means which amplify the particular signal with the particular gain. For example, if I say the 2 volt is amplified with the gain factor of 3, then it will be amplified with the gain factor of 3. So now, but in some application we need to amplify some of the frequency components with the different gain factor. And some components with different gain factor. Such type of amplifier is called as non-linear amplifier. For example, you have seen in the music system, we have some in the music system we have so in the music system, we have some frequency component, this bass buzzer. We can vary the frequency component by varying all those. So we can particular frequency we can increase and particular frequency we can decrease. That is actually now one of the application of the non-linear amplifier. The diagram for the non-linear amplifier is shown here for your figure. Here actually you can see the capacitor is connected in series. That means it will allow high frequency component, and diode is also connected. So and now our problem statement is something like this. I have waveform something like this. I have waveform of one is 2 volt of same frequency, other one is of higher amplitude of same frequency, higher amplitude of same frequency. I want to suppress this one and I want to amplify this low amplitude signal. I want to amplify low amplitude signal and I want to suppress this one high amplitude this one signal. For low amplitude signal, this diode won't be able to conduct. This diode won't be able to conduct. That means low amplitude signal, frequency, and I am talking about amplitude, not frequency. Low amplitude signal will pass through this operational amplifier and get amplified. For high amplitude signal, this diode, one of the diode will be conduct during the positive cycle, other diode conduct during the negative cycle. So the signal passes something like this. Without it means it bypasses our operational amplifier. So that is the it bypasses the operational amplifier. So by like this I can suppress this one component, I can amplify the other component. This is called as a non-linear amplifier. So my dear students, we have completed all the application of our operational amplifier. With this our operational amplifier concept is completed. The next one is called as wave shaping circuits. The wave shaping circuits you will see 555 timer and monostable and astable multivibrator. With that our first module will be over. Thank you. Dear student, with respect to this our monostable multivibrator, we have one problem here. So he says in the problem, refer to the diagram. So trigger input is given. At pin number 2, this is the pin number 2 of the IC. Trigger input is given, and trigger input is driven by symmetrical pulse waveform of 10 kHz. Symmetrical means something like this. Symmetrical of he says this is the frequency of this one is 10 kHz. 10 kHz. Determine the frequency and duty cycle of the output waveform. We are measuring the output waveform here. You have to measure the duty cycle. Now frequency of the trigger waveform. Frequency of the trigger waveform is 10 kHz. The time period now. Time period you will get is equal to 1 by 10. The time period you will get here is 1 by 10. 1 by 10 kHz, that you will get around 1 by 10 kHz, you will get around 50 microsecond. So now total time period between two successive leading or trailing edges, that is two successive leading and trailing edges is 50 plus 50, that is nothing but you will get 100 microsecond. That is nothing but 100 microsecond. You will get 100 microsecond. Now here you can see this is the trigger output 100 microsecond. Sorry, trigger waveform of 100 microsecond of time period, that is 50 microsecond for on and 50 microsecond for on. And this is the, see here, one more thing you have to make a note. One more thing you have to make a note. This is the trailing edge of the trigger. So initially our output is 0. Our output is 0. Initially our output is 0. During the trailing edge, it becomes on. So till what extent it will remain on? This is stable state. Remember, this is stable state, and now it is going to unstable state. Till what time? So you have to find out it here. You have to find out it here. So you have to find out it here. So as I said, this is a negative edge. These are the negative edge. So output is low and output going to I state, unstable state. So initially our capacitor charge is 0. It is going to charge till 2 by 3 of a VCC. So what do you mean by 2 by 3 of VCC? That is calculated by the formula RC. That is calculated by the formula RC constant. So that is calculated by the formula our RC constant. You can see here RC constant 1.1 RC constant. You can see here it is 1.1 RC constant. When you calculate this one, that is nothing but 1 by 110 microsecond. It is 110 microsecond. So here you can see this is 2 by 3. This is 2 by 3 VCC. To reach this 2 by 3 VCC, it will take 110 microsecond. That is, see, it is 50. So it starts from here. So this is 50, this is 50, 100, and somewhat here 110 microsecond. After that, it will discharge. After that, it will discharge and it will remain in the lower state. It will remain in the 0 state. But now it will remain in the stable state. Now it will. To move into unstable state, it needs one more negative cycle. So you can see here, this is the one negative cycle. Here it went to unstable state. But this is one more negative cycle, negative edge. Here you can see it is in the I level voltage. That is, it is in the logic 1. It is not in the logic 0. When it is only in the logic 0, then only you can trigger it up. So next negative edge is here. That means till here it remains 0 voltage. At this stage it will get triggered up once again because of a negative edge of the trigger, that is called as poking, and it will go to once again capacitor will going to charge once again. That means, so here output will remain till here in the output stage, logical 1 state, and it will go to logical 0 state, and it will remain logical 0 state till here, and once again it will go to logical 1 state. So what is the total period, time period, total time period of this waveform? Total time period of this waveform, output waveform, is it takes, if you calculate here, 200 microsecond. So frequency is nothing but 1 by t, 200 microsecond is nothing but 5 kilohertz is the frequency, and you can calculate duty time cycle also. Duty cycle also. Duty cycle is nothing but T1 divided by T1 divided by total T. Total T is equal nothing but 200 microsecond. T1 is nothing but 110 microsecond. That is 110 divided by 200. So what you will get? 100 by 10 by 200. You can see here. So you can see here, if you that you will get 55%. So duty cycle is 55%. So dear students, with this I have completed module 1. So we have one more problem here. You can see one more problem here related to the astable multivibrator. Please go through it. So if you have any doubt, you can come back to me, or you can SMS, you can text to me. I will answer your query. Thank you. So this is the problem related to astable multivibrator, where we are computing high time and low time, and you are calculating frequency, and this is the output waveform.